Welcome back, everybody. This is part 2 of example 5b. In part 1, you would have seen us create predictor variables for the analysis, examine univariate descriptive statistics, examine bivariate Pearson correlations, and then examine bivariate relationships between each predictor to be considered, age, grip strength, gender, and three-group dementia status, in predicting cognition in separate models. Now we are ready to put them all together, picking up in example 5b on page 12 with a joint model that features all of the effects from the previous separate models. So we have a linear effect of age because the quadratic effect did not contribute significantly. Likewise, we have a linear effect of grip strength because its quadratic effect did not contribute either. We have a linear effect of binary gender because that's all it could possibly have. It's only the difference between the 0 group and the 1 group. And likewise, we have linear effects of these binary predictors that distinguish the none versus future groups and then the none versus current groups. So all in all, I am estimating 5 slopes. And I'm going to demonstrate how to get the joint contributions of 2 or more slopes at a time to be able to look at their significance via an f-test as well as a measure of their effect size via semi-partial correlation squared. Both of these things are able to be done within one set of statements within SAS. Stata requires a little bit of extra legwork, as we'll see in just a second. So picking up here on page 12, here is the SAS code that we'll be examining. So cognition is the outcome. We have all 5 slopes being entered into the model so that we have 5 predictors, 5 slopes being estimated, as well as the fixed intercept, which is always there. I am using 3 different contrast statements here to give you examples of how you would ask for the joint test of significance and its corresponding effect size for more than one slope. The first one is a pedagogical exercise because this one is already given to us. What I've done here in the first contrast statement is recreate the f-test for the model. That is, I have entered in each slope that the model is going to be estimating, one each, and each of those is separated by commas to denote its degrees of freedom. So this is a 5-degree of freedom test for whether or not that set of 5 slopes simultaneously significantly predicts the cognition outcome, and that is exactly what the model f-test and R-square are going to tell us. Here are 2 examples of subsets of predictors that we might want to examine. So for instance, if we have a contrast statement that includes the 2 slopes related to dementia group, that corresponds to what is known in ANOVA language as an omnibus main effect of group. So we're lumping together the 2 slopes that we need to be able to distinguish the means of the 3 groups. And so these 2 slopes recreate all 3 possible pairwise differences. I'm lumping them together so that I can talk about the effect of dementia group as a unitary construct, even though it takes 2 slopes to describe the full effect of dementia group. As an example of another set of variables I want to lump together, let's say that I wanted to examine how much of the variability has to do with demographic variables such as age and gender. So I can lump those 2 together to get a test of that if I wanted to. I have also estimated all 3 possible dementia group differences. The first 2 are given directly as slopes in the model, so I wouldn't need these, but I've included them here for pedagogical purposes. And the last one is the one that the model does not provide directly. It provides the difference between the non-reference groups as a linear combination of the slopes differentiating them from the reference group. So if I want future versus current, then the slope that separates out the future group gets the -1, and the slope that separates out the current group gets the 1. And again, I'm saving the results of these analyses to SAS datasets so that I can compute effect sizes for each of these slopes. And in this statement, I'm asking for not only the regular solution for fixed effects, which is known as the parameter estimates table, but also this additional set of estimates I requested via estimate statements, which is known as estimates. Stata code to do all of these things looks somewhat similar. we have, looks, I forgot my level 95 here, my bad. We have cognition as the outcome. We have each of the 5 slopes with a C in front of it. C dot allows us to do math on those things. I have recreated the F-test for the model using a test statement. So that's the analog of the contrast that's used up here in SAS. The difference is that each slope to be tested is explicitly tested against 0 and separated degrees of freedom into separate parentheses. So this is 5 sets of parentheses. That's how I know it's a 5-degree of freedom test. We're testing each of the 5 slopes jointly as a whole to recreate the model F-test and corresponding R-square. The test for the omnibus, as it's known, or overall effective dementia group, is right here. So testing just those 2 slopes by themselves. And then the test for the 2 demographic variables by testing just those 2 slopes by themselves. So you're allowed to lump together any slopes that you want to be able to talk about how these predictors contribute jointly any way that suits you to answer your research questions. We have lincoms here as the analog to the estimate statements. These allow us to get the specific group differences between the dementia groups. The first 2 are redundant with the model parameters. The third is the necessary one to ask for the linear combination. And then I'm also asking for semi-partial eta squares for some of the terms. I can get them for these 3 in particular. The ones that they'll provide for these 2 dementia groups are not valid, as we discussed at the end of the part 1 video I just finished, but I do have to have them in here so that the correct partialing or semi-partialing, as it's known, is done with respect to these predictors. So here's my output from SAS. First up is a test of the model. So we have 5 slopes in the model. Given our total sample size of 550 individuals, that means that our corrected total here is 549 because we always have the intercept in, that's the missing one. So that means we could have had 544 more slopes possibly estimated in this model. The 5 slopes that we did include, however, captured this much information, and if we divide this model sums of squares by the number of slopes it took to get there, we get our mean square for the model. So you can think of that as variance explained, so to speak. Not exactly, but close. This bottom one here is variance left over. And so 88 is what's left relative to the 190 or so that we started with. That is a reduction of 28%. So the overall set of 5 slopes has accounted for 28% of the variance in cognition in this example. And if I take the square root of that R-square, that gives me the correlation between the y that is predicted by this 5-slope model and the real one. And that prediction is significant as indicated by my F-test right here. The SAS output also generates the sums of squares that are attributable to each source and then computes semi-partial eta square as the sums of squares for each divided by the sums of squares total. I have a note here that although we could talk about these particular semi-partial eta squares, these are the part of the R-square that each of these predictors is uniquely accountable for. So they each get about 2%, the total for the whole model being 28%. But I have a reminder here that we can't use these ones for the dementia group's contrasts. As we discussed in part 1 of the video, because these contrasts are related to each other, they have a common reference group, the semi-partial eta squares that you would get across contrasts are going to sum up to more than what dementia group contributes as a whole. So there's redundancy in these terms because we're comparing the same groups. So we do not want to use those semi-partial eta squares as effect sizes for the dementia group contrasts. What we can use, though, are the ones that are going to be created from the contrast statements. And so that's the point of asking for them. We get a sums of squares for the 2 slopes as they work together. We get an F-test for whether those 2 slopes are significantly different than 0. That describes the overall effect of dementia group. And then we also get the corresponding semi-partial eta square. So about 18% of is of the total variance accounted for. It's not a proportion of proportion. I'm trying to word this correctly. 18% of the variance in cognition is attributable to dementia group. We had 28% of the variance total. So a huge chunk of that is due to dementia group specifically. So the total for the model is here. The amount that's due to dementia group is here. The amount that's due to the demographic variables is here, about 4%. And that those two variables do have a significant contribution to the model as given by their F-test. So when you ask for contrast statements in SAS, you get both an F-test for those slopes lumped together, that's what's shown in this table, as well as an effect size via semi-partial correlation squared. So eta, by the way, is synonymous with correlation, that you can think of them as telling you the same thing. In terms of stata, to be able to get these semi-partial eta squares, you have to estimate a reduced model that does not have the terms you're focusing on to see what the difference in the sums of squares would have been. So in order to get the sums of squares attributable to each of these contrasts, I had to fit a model that doesn't have the terms. So for instance, leaving out the two dementia group terms, I then get the sums of squares from that reduced model. If I compare it, take the difference relative to the sums of squares to the present model, so where that figure came from is the present model. The total came from the present model. So I'm estimating this reduced model to be able to get this term right here. So that way the difference tells me how much of it is attributable to the two terms that were not included. If I do the math here, it works out that the semi-partial correlation squared is what we found directly in SAS. I did the same thing to demonstrate the effects of age and gender, fit a model without those, got the reduction, the semi-partial correlation. Looks like that is a typo that I need to fix. I did not change that on my copy. I will fix the handout and repost. This should be a different number than what I just found up here. But I did change this one, which is the correct semi-partial correlation for those two parameters. In terms of the model, here's our solution for the fixed effects. So these are the coefficients that you get just from asking the model to be estimated. So the fixed intercept is always the expected outcome when all your predictors are 0. So based on the centering points of the predictors, cognition is expected to be 29 for somebody who is age 85 with 9 pounds per square inch of grip strength, who is a man, and who does not have dementia. That's our "you are here" sign reference point for the model. Each of these effects, because they are not part of interactions, we can think of as marginal main effects. So each controls for the contribution of the other predictors, but each of these slopes holds for everyone in the sample. So for instance, for every year older you are, cognition is predicted to be lower by 0.4. And that's a significant effect given by the p-value here. Just to recall, the way we get to the p-value is to take the estimate divided by the standard error. So this is the estimate for the slope. This is the standard error for the slope. Estimate divided by standard error gives you this t column right here. And then the p-value gives us where RT falls relative to the critical reference distribution that would be given by the denominator degrees of freedom. So the software figures all of that out for you. A p-value of p less than alpha, so less than 0.05 here, tells us it is sufficiently unlikely to have observed a slope this large if the population slope were truly 0. So for every year older you are, cognition goes down by 0.4. For every pound stronger you are, cognition goes up by 0.6, and that is also a significant effect. This is telling us that there is a significant gender difference. So because the men are the 0 and the women are the 1, A negative slope is telling us that the women who are the 1 are lower. So women are lower by 3.6 than men, significantly so. So we have significant effects of age after controlling for everything else, significant effects of grip after controlling for everything else, significant effects of gender after controlling for everything else, and last but not least, the effects of dementia are significant after controlling for everything else. Relative to the none group, the future group is 5 points lower, which is significant, and the current group is 16 points lower, which is significant as well. And if I take the difference between these two slopes, that works out to be almost 11. That gives me the difference between the future group and the current group, which is provided from the estimate statement results down below. And note that these two are a repeat of what's already in the table because they are just given by one slope that's in the model. I then took these two tables of output, concatenated them, and calculated Cohen's d and an R effect size from the t-values that were given, and printed those again. So we can talk about effect size for each of these terms in either a d standardized difference metric, which is useful for the predictors that refer to group differences, or in an R correlation metric, which is more useful for the quantitative predictors. So these individual effect sizes are necessary to be able to describe in more absolute terms how strong the relationship is between these predictor variables and the outcome after controlling for the other predictors. We could also calculate standardized slopes. So to do that, we would run the same model in procreg instead of procglm, because procreg has an option available to create standardized slopes. Unfortunately, procreg does not have estimate statements or contrasts, which is why we're not using it primarily. Stata, you can have the regress command and add the beta option, and that gets you standardized slopes. So I have the output from procreg here. The unique information that is provided by procreg is an adjusted R-square. So let me fix that. That is the wrong one to be highlighted. Adjusted R-square is something that's only provided by procreg, not procglm, as well as this last column, which provides standardized slopes. So this is another way of expressing the effect size of each of these individual terms. These numbers are close to the R's that I calculated using the T's, but they're not the same. Standardized slopes are most useful for quantitative predictors that have linear effects only. If you have interaction terms, they become ambiguous because order of operations matters in standardizing, so they tend to be less useful in those situations. I personally like the idea of semi-partial R-square, these things, because they tell you how much variance they account for uniquely, and I think that's intuitive given the use of a model R-square to describe the overall joint effect of these variables. So one way that you can get standardized slopes without having to switch to a different procedure, for instance, is to create z-scored versions of all of the variables in the model. So I've demonstrated how to do that in SAS. I am first creating copies of the variables that have a letter z at the end of them. So just creating a new column that's a copy of the old column, because I'm then going to feed those new copies of the variables into this proc standard, which creates z-scores for us. And so these columns will now have a mean of 0 and a standard deviation of 1. Stata does the same thing with the std function with an egen. And so after I create z-scored versions of all of my variables, I could estimate the usual procglm or the usual regress using all the z-scored versions, and then the slopes that I get out of the model are directly standardized slopes. That means that I would have my usual cadre of estimates and contrasts and all the other things at my disposal, which is very convenient. So the extra linear combination of the two slopes for dementia group that I would not be able to get, say, out of proc reg directly, I can get if I'm willing to standardize the variables ahead of time. So the last part of this, I wanted to compare what the effects of each of these predictors were in the separate models, so their bivariate effects as they are known, versus their joint effects, unique effects in the combined model. And so I have these estimates tabled here so that we can compare them more readily. And generally speaking, the effects are stronger when only that predictor is in the model than they are when all the predictors are combined. And we would anticipate this to be the case because these predictors are all related to each other to at least some extent. So whenever predictors are related to each other, the effects that they have uniquely when they are combined in the same model are going to differ than the effects that they have bivariately when they are each in their own separate model. I also have provided all the possible ways that one could talk about effect size here in one table. So we have standardized slopes. We have standardized mean differences in D or R that we could compute using the t-test statistic for each. So I've given the formulas here in the table note. We also have semi-partial correlations for the variables in which we could calculate that. We have R squares, which is the square of the R computed here. And then we also have the squared semi-partial correlations. So I've included all of these just to show you that they're going to converge onto the same ideas, but they're not going to be exactly the same. As a colleague of mine once said, there really is no such thing as a standardized effect size. So be careful and thoughtful in which one you decide to report, and make sure that your readers know exactly how you found it. So in providing your effect sizes, describe how it was computed very specifically. Giving these formulas or giving the code is a good way to make sure that you're very transparent in describing how you estimated these effect sizes. And as usual, I've included a sample results section. One of the things that would be expected in a general linear modeling analysis is to report a table that would look like this, where you would summarize descriptive statistics for each of the variables in question. So I have mean, standard deviation, minimum, and maximum here in the bottom of the table, as well as the Pearson correlations between these variables. I'm not able to include dementia group in here because the contrast for dementia group that went into the model don't have the same interpretation when they're viewed separately as when they're viewed jointly. And note that I'm only reporting one correlation. I don't have both halves of this correlation table because they would be redundant. And here are some words that you can use to describe the results of the analyses. So I've summarized the separate analyses here in this paragraph, and then I've described the results of the joint analysis with all the predictors in this paragraph. And I'm noting that just describing what happens is typically insufficient. You would also want to make sure that you tie your description of what happened explicitly back to the research questions that motivated your analysis. So give the story as answers to those questions, and that will help provide the necessary context for your readers to follow you. So that is it. I hope you all have a good break, and I will see you in a little while.